look at we're going to look at a beam analysis. So looking at beams, how they're loaded, and how they react to that. So if we look at a structural member, if we talk about a beam, we're really talking about a structural member that basically is applied, that the load is applied transverse to its length, perpendicular, basically. So specifically floors, roofs, we refer to the floor joists, stringers, floor beams, girders, all of those things we're going to treat and kind of throw in a large category called beams right now. So the beams are designed to carry a shear and bending moment caused by those design loads. Now, the bending moment is basically how it dips down, and the shear force is a force perpendicular to that beam along the way. All right, so first things first, we got to chase the load. We talked about this in the last video, in the last PowerPoint. Now, the loads are initially applied to the surface itself, be it the floor or the roof. That load's then transferred to the beams, which transfers the load to another building component. So here we go from the beam, from the floor to the beam. That beam's sitting on a girder. That girder is applying its force to a column. The column goes all the way down to the foundation here, that footing down there, which is transferred to the soil. So we're chasing that load all the way down. But most importantly, it's not going anywhere. This is a building, we don't want it to move. So therefore, it's in a state of static equilibrium. So all the forces applied, they counteract each other, so the object remains stationary, no acceleration. It has to be in static equilibrium to successfully carry those loads, or else it's accelerating, and there's lots of other issues. So the load force applied to the beam from the floor then must be resisted by the beam's supports. So if we have applied load here in the middle, we have reaction forces, action force, reaction forces. Now, in the pure physics sense, action-reaction forces between two objects. This is not necessarily in that sense. This is a support force that happens because a force is applied for it. This is more cause and effect, not Newton's third law, action-reaction forces. But the term is still very, very common in this when we use it. So they are vectors, so direction matters. They have a magnitude and direction. So in these, the reaction forces we're going to look at, the supports that we're going to look at, we have the shear reactions, which is a linear force. We also have a rotational reaction, or called a moment reaction, a twisting or a torque, so preventing something from spinning about an axis. So all of these forces have to balance out. Now, you could have three different types of supports, and if you had POE, this may look familiar. A roller support is going to provide support in one direction, perpendicular to whatever surface it's on, but it's going to let it move side to side. A pinned connection is located. It is fixed at one location and lets it rotate, but it's going to provide two reaction forces, one horizontal, one vertical. A fixed support provides all three. It provides horizontal support, vertical support, and it prevents it from twisting. So it provides a moment reaction as well. So depending on how it's supported, depends on how many reaction forces we need to put at that location. We can look at a couple different beam types. Most commonly, we're going to look at a simple beam, which has a pinned connection on one side and a roller on the other. But you could see a continuous span where you have several supports along the way over multiple. You could see a cantilever, which is fixed at one end, fixed at one end and left hanging out the edge. You could see a fixed beam, which has a fixed ends on either side, so it provides moment reactions on either end. You could see a propped, so fixed at one end, possibly supported on the other. Or you could have an overhang, where you have two supports, but the beam itself overhangs all of these. All the different scenarios. Now, the concepts and the ideas and the science behind this still applies to all these scenarios. We're mostly going to look at simple beams, however. An applied load somewhere in the middle or distributed with a pin at one end and a roller on the other. So if we don't have any horizontal loads, which typically for the examples we're going to look at, we're going to limit ourselves to just vertical loads on this. This horizontal reaction, it wouldn't be reacting to anything, so there probably would be no horizontal force there in this case. There could be if we had one, but in the examples we're going to look at, we won't have to consider that. Next slide. All right, so to codify this a little more specifically, the fundamental principles of equilibrium, basically all the forces in the y direction, the vertical directions, have to add up to zero. All the forces in the x direction have to add up to zero. All of the moments, so all the twisting about any point, has to add up to 0. So those are the ideas that we're going to apply to the scenario as we go forward. And when we keep referring to a moment, basically it's created when a force tends to rotate an object. So you have a force at some perpendicular distance to a point of rotation. Here it's the wall. So the magnitude of that moment is literally the force times that perpendicular distance. If those two aren't perpendicular, we need a component of either one. So force times perpendicular distance is going to be our moment. All right, so in the next video, we're going to look at actually sketching and solving for an example of reaction forces and beam diagrams, etc.